Good morning, chat. My name is Penbu, and I'm the programming, puzzle gaming, and music making vtuber on Linux. And today, yeah, I guess this counts as a puzzle game. All right, we are puzzle gaming. March 14th, 314, Pi Day. Pi turn, I welcome in. Pi, if you don't remember from school, is the mathematical constant that refers to the ratio of the diameter of a circle to its circumference. Diameter being... where is my cursor? Diameter being this part, and the circumference being this part. So it has a very, very fundamental, very important role in mathematics. As I said in my message earlier, I do have some pie of the pizza form with me today. I might be eating it as we play. But today, our game is Euclidea. It is a game where you try to construct things using a straight edge and a compass. And this construction method is something that's been known in antiquity. Alright, well, let's get into it. So it's 120 levels, from very easy to really hard. And really hard is not an exaggeration. There are some of the some levels here that I have not been able to go through. 11 tutorials, 10 innovative tools, automatic verification of solutions, explore mode and hints, and dynamic geometry in action. So we will see all that. Alright, let's get into it. So we have all these Greek letter levels. I think I managed to get all the way to somewhere down here, maybe with a little bit of help back in the day. We'll see how far we get to this time. But the first one is pretty easy. I have an equilateral triangle. I'm going to make this a little bit bigger too. Construct an equilateral triangle with the given sides. The construction must be exact. Guessing even very close points does not count as a solution. An equilateral triangle is a triangle that has 3 equal sides, and also as a consequence, 3 equal angles too. Hence equilateral. And so we're given this line here. And so how do we construct one? Obviously, your first thought might be to do this, but that's not going to be exact. How do I undo? Reset. But we can use a compass, so the circle tool here, because we know that from the center of a circle to its edge is always going to be the same length. So if we put 2 of these together, then we know that this point where they intersect has to be the same as this length here. We're going to draw a line from here to here, and another one from here to here, and this is our triangle. All 3 angles of an equilateral triangle are always 60, the hint. And so now we get all these stars, one for completion, one for the minimum number of tools, and then the other one's minimum number of real compass and straight edge actions. Okay, now we get another one. You can receive one more hidden V-star if there are several possible objects that satisfy the statement of a problem. All of them should be constructed simultaneously. Construct the second equilateral triangle with a vertex that looks in the opposite direction. And so here we have some symmetry. We can construct the same triangle but pointing this way. Now we have this one too. And now we've gotten 4 stars on this. Okay, next one. Construct an angle of 60 degrees with a given side. If we remember from the last one, an equilateral triangle has angles of 60 degrees. And if you remember from school, a triangle, all of its angles add up to 180. And so 180 divided by 3 is 60. And so we can do the same thing, construct an equilateral triangle, but just don't put in one of the sides. Let no one ignorant of geometry enter here, Plato. And we can construct another one, very similarly, this way. we go. I'm going through these quickly. Hopefully it's not too fast. But I'm sure the later ones won't be as quick. Tutorial intersect tool. If it is hard to hit the required intersection since the lines are too close to each other, use the intersect tool. One object, a circle or a line. Then the second one, to practice construct the intersection of the given circles. So these are too close, but we can look at the intersections for these. And we are looking at the ones for just the circles. So it's not that one actually. It's this one. And then also the one over here. Yes. Every intersection has a story. Catherine Dunn. Next one. Perpendicular bisector. Construct the perpendicular bisector of the segment. So there are two parts to this term. Perpendicular meaning at 90 degrees from the line segment, and bisector meaning split in two. Split in two being equal parts. So this is a line that splits the line segment into two equal parts, and it is at a 90-degree angle from the line itself. And so how do we do that? I don't know how to explain it. I kind of just know how. It's you do this. Okay, so let's break that down and see why that works. We know that from here to here is the same angle or same length everywhere, and from here to here is the same length everywhere. And because you have two similar circles, both at points away from each other, you have symmetry, and the point where they intersect is the middle. Yeah, something like that. I don't have a rigorous proof of this, but that is how that works. Tutorial Perpendicular Bisector. You have discovered the Perpendicular Bisector tool. Click sequentially on 2 points to see how it works. We will do that. We have this bisector tool here. And now we click on 2 points, and that just does that all for us. Note that the perpendicular bisector tool costs 3 elementary moves, as we had done earlier. You need 2 circles and then the line. And this actually becomes important, because there are some puzzles where you will be able to reuse certain constructions to get down lower elementary moves, but it'll use more L moves. Midpoint. Construct the midpoint of the segment defined by 2 points. So we have this. We can draw a line between them. And then we can do our bisector to get the midpoint, or the middle, right? Because bisector splits it into 2 even points. And then we just take the middle. Alright. There are no other ones, so I think that's that. Circle in square. Inscribe a circle in the square. Well, it seems easy. But first we gotta figure out where the midpoint is. And so one way we can do that is to make this cross here. This point is the middle. And then... well, and we need to be exact, so we can't just estimate here. So we need to find the midpoint here. And we can do that by doing one bisector here, and then attaching a circle to that intersection here. Oh, we can do better. Okay. Let's try that again. We can do the bisector. And we actually don't need the second line, the second diagonal. We can do it with just one. And then we have the circle going out from the middle all the way to the edge. That gets us our L. I guess that gets us our E too. Okay. You can't fit a round peg in a square hole. American proverb. That reminds me of that that one, I think it was a TikTok, where the guy had a kid's toy where he had to put the blocks in the holes, and all the blocks ended up fitting into the square hole. By the way, if you want to try this game for yourself, the link is in the description. That's Euclidea.xyz. Tutorial, move tool. Pascal's theorem states that if a hexagon is inscribed in a circle, then 3 points of its intersection, 3 points of intersection of its opposite sides lie on a straight line. Use the move tool to see how the theorem works. Just drag the blue points. Alright, try to understand how this works, what this says. Then the 3 points of intersection of its opposite sides lie on a straight line. Actually, I guess we'll just see it's here. So if we move these points here, then if you extend... Oh, I'm still playing around with that. Our nature consists in motion, complete rest is death, Blaise Pascal. So we have our hexagon here. And it's saying that the lines, if you extend them, intersect, and you end up with a line this way. I'll try to shrink that a little bit. I'm not sure what the application here is, but sure. Alright, next one. Rhombus and rectangle. Inscribe a rhombus in the rectangle so that they share a diagonal. So a rhombus is a quadrilateral, a four-sided shape that has all equal sides. So a square is a rhombus that has angles of 90 degrees, but rhombuses in general do not need to have 90 degrees, and most of them don't. Okay, so it has to share a diagonal, which means this is going to be the diagonal for one of them. How do we do that? I guess we can start with maybe this, finding a center point here. And then we can just draw circles or something. How do I undo? This is how I undo. Let me find the midpoint this way. And so then we can draw a circle from here to here. At this point I'm kind of just guessing. But if we have two equal sides, so here and here, that means that from this point until wherever we have an equal side, what was it? So it's a circle, right? That means that if we extend it to an edge, that's going to be the same, the distance from here to here is going to be the same as here to here because it's a circle. The radius is always the same wherever you are from the center all the way to the edge. Ashlucia, welcome in. Happy Pi Day. Yes. We are making a bunch of circles. Current challenge is to find a rhombus and rectangle. And this is the first one that I'm actually somewhat struggling in. Okay, I'm gonna reset this. This one's too large. I'm gonna undo that. So if we do bisector... Oh, okay, I see. Right. So rhombus, because of the way this works, these two angles are equal and these two angles are equal. Which means the midpoint between this diagonal has to be where this axis lies. Which means we can find a bisector of this line. And then where they meet here should be our our edges. There we go. Alright, I guess we can be a little bit more efficient. I wonder how. Oh, because we didn't need to do that, right, okay. And do that again. We actually only need to fill in the ones that we don't have. There we go. And then we can build the other one. Because we have symmetry here, so we can build the other one. So we take the bisector here. And then it's a little bit, having a little bit of trouble figuring out what we have here, but I think if this was, so this is diagonal here, that means we're reaching out to here. And then we have this going to here, and that's our second rhombus right there. Nice. Without mathematics, there is no art. Luca Pacioli. Next. Circle center. Construct the center of the circle. Note, L and E are goals are independent. To get 3 stars on this level, you'll need to solve it twice. One solution with 2L and the other one with 5E. So at minimum, we have 2 tools that we need to use. So we'll start with that one. Hints. You already said that. So I think what we can do is that... maybe not. We can draw a line, and we intersect with this line from anywhere. And then, so that's one tool. And then here we know the center of the circle. I'm gonna reset. We can't find the center that way. We can kind of... no, we can't do it that way either because we need proper points. Maybe the approach here is just to get something working, and then we can go from there. Okay. So we create one here, and we create another one here. Maybe bisect a chord. Yeah, that's what I did earlier. But okay, let's try that. Oh, I need to put an intersection point here. We bisect the chords, and then we need to do this again. Find the middle. But that's yeah. So our solution here is 3. We need to go down to 2. Okay, restart. So at least we've earned 1 star. So we can start with a... I think we do still have to start with a chord or something. MKH2 Cat Lover, hello, welcome in. Happy Pi Day. Goal here, trying to find the circle center just using these tools here. We got there with 3 tool uses, but we're trying to get down to 2. Or try to get, using just compass and straight edge, 5 tool uses. I think you have to start with a chord, don't you? Because otherwise you don't have any points of reference. But then what can you do with it? That's 1. 2. No, that doesn't do anything. Okay, chord again. And then... how do you get 2? Okay, maybe bisecting a chord isn't the way to go, but you do have to find the middle somehow. So maybe you have to is it just 2 bisectors? But then you aren't guaranteed to have it exact because you aren't. You can't be exactly on. No, it surely doesn't let you do that. No, that's not exact. Okay, whatever. But if that's the case, then what we can do is we can take 1 and do the same thing, 2, and then reuse it. It's not proven. Yeah, maybe. It's a lot easier to, what was it? It's a lot easier to find an exact point if you have an intersection to go with. But yeah, I guess if you have an accurate enough line or something, you could make the argument for it. Or maybe I'm not well versed enough in compass and straight edge construction. But okay. So one of the tricks here, I think, is that we can reuse one of the points here. Because one bisector uses 3 elementary moves, but we can get down to 5. So what are we looking at? So this is the bisector. And then we had earlier 2 bisectors, which means that we can actually maybe bisect this one. Yeah, no, I was right the first time. We do this, and then you add the lines together. This one here. It moves. Undo. And then also this one, I'm gonna get this straight, this one here. So just make sure my notifications are off. Let's do that before stream. Okay. That's all good. And so this point here should be the midpoint of the circle. Alright. Nature is an infinite sphere of which the center is everywhere and the circumference is nowhere. Also Pascal. And there's only 1 midpoint, so there's nothing left to do there. Inscribe square. Inscribe the square in the circle. 1 vertex of the square is given. So this is kind of the opposite of what we did earlier, where we put a circle inside of a square. But now we're putting the square inside of the circle. One property that we know of squares is that all sides have to be of equal length. So we know what the other one looks like. Which means this is the direct opposite of this vertex. And then we also know that because it's 90 degrees, squares all have 90-degree angles. We can use a bisector, a perpendicular bisector, to calculate 90 degrees and then put points here and here and match up the square this way. So that's with the 6 tools. And now we can try to get down to 8 elementary moves. Alright, reset. I think we still get this. We're gonna put a point here. But how do we get a second one? Because yeah, sure, we can do this and we get this point, but then that's the same as using the bisector tool. So is there another way to calculate 90 degrees? So doing this is useless because that's exactly the same as the circle itself. And we can't use another bisector because that's 3. Well, what are we at right now? We are at 1. And we need 4 to draw the square. So we're over by 1, which means we're able to reuse something. What does this here get us? Nothing much. Also, I don't think there's anything here. Because this gets us, what, 60 degrees here, 60 degrees there. Yes, so this is 60 degrees. And we need another 30 degrees. 30 degrees is 60 divided by 2. We can cut it to 60 in half. But where can we do that? So we're gonna need it over here somewhere, somehow. We're already at 4, so that's not gonna cut it. I think we still do need this line here, though. Because otherwise, how are we getting the other side? We can try making a bunch of these circles here, but oh, actually, is this? No, that's not exactly. Yeah, that doesn't go through the middle. I remember this doesn't actually. Oh, maybe it does. 1, 2, 3, 4, 5, 6. Maybe it does go through the middle then. Okay. So then we do that. Is this 3? And this is a line. I feel like we've already used... Yeah, this is 8. Is there anything we can optimize here? So we have to have this circle because otherwise we have no place to start. And then where else can we go from here? We have to have this circle, I think. Because otherwise we have no other reference points. And then we have to have this one so that we get the other side. Otherwise, we get the other side through this way. Can we do this? No, we can't do that. But if you do this way, then you get the same thing as the bisector. Okay, we're gonna come back to this. Move on. Angle bisector. Construct the line that bisects the given angle. Bisect again, meaning break up into two parts that are equal. So we need to have a line here that splits these up into two equal angles. One way we can do that is take a circle and then bisect this here. Probably the way then. And the reason that works is because, again, with a circle, every length from the midpoint of the circle is the same length. So this and this are going to be at the same length away from the intersection points. And then if we bisect this line segment here, imaginary line segment, and we get it perpendicular, that means we're splitting up this imaginary isosceles triangle. Okay. Moving on. Trial angle bisector. You have discovered the angle bisector tool. Click on any point on a side on the vertex and on any point on the other side. So this is really handy. We just make the angle there. Note the angle bisector tool costs 4 elementary moves. Again, as we saw, 1 circle and then 3 from the bisector tool. Intersection of angle bisectors. Construct the point where the angle bisectors of the triangle are intersected. I can't remember if this is where the center of gravity of the triangle is, or if that's somewhere else. There is, if you can figure out the center of gravity of the triangle by, was either the side bisectors or the angle bisectors, and I think it might have been the angle. But easy way, we can do this with 2, and then we find the midpoint. So that gets us, so that's 2 tool uses, and we need to get down to 6 elementary moves. Triangles have too many centers, yes. And we can do that by reusing one of our circles. We can do that by reusing one of our circles. And that's not how we reuse a circle. No, this can't be right. That definitely does not look like the center. And this probably isn't the center either. Yeah. We can reuse a couple of circles. But how do we do that? So I guess we use the shorter side. The intersection there. So this gets us not quite. Oh, actually, you know what? Maybe that is how you reuse it. Take the shortest side. So we do this, we do that, and then now we have a circle from here. No, that's not quite right. We need it on the other side. I think we make a circle here to somewhere. So now we can make this here. So this is the bisector here. And then we can reuse... Where is my other circle center? So this is the circle center. And if we draw something from here to there, we're at 5 now. And then we have our intersection. Well, it would have been the extension from here to here, but we don't have that. And it surely isn't this one here. I don't think this is it. We're gonna come back to that one. Angle of 30 degrees. Construct an angle of 30 degrees with a given side. So as we discovered before, an equilateral triangle does have an angle of 60 degrees. And so we can draw a line from here, and this is now a 60-degree angle. And we can bisect that to get 30 degrees. And apparently we can be even more efficient. But this is, I think, how you construct one. Oh, but then we don't actually need the other line, we just need to bisect it. Okay, so that's 3 tool uses. Inspiration is needed in geometry just as much as in poetry. Alexander Pushkin. But then we can do the other side. This gives us the 2V. And then we reset. Now to try to figure out how to do this with 3 elemental moves. How do you do that? Because this is 1. This is 2. Ah. Because then we create the bisector here, I see. There we go. No, that's not quite right. That's 1 more than we needed. But I think that is getting there. Because I think we do have to reuse one of the circles to be a bisector. So we have some arbitrary point here, sure. We have an arbitrary point. And an arbitrary, that's not going to do anything. We can go into explore mode. So what does this look like? So we know this is a bisector. Now how do you get down to 3? How do you construct that? This might be another one where we come back to it. I have no ideas here. I can get down to 4, I don't know how to get down to 3. I can't figure out where we can share a circle. Okay, we're gonna come back to that one. Double angle. Construct an angle equal to the given one so that they share one side. I do remember that I actually have 100% at this level. Or rather, this level set. Just trisect the perpendicular forehead. Yeah, if only we could do that. Construct an angle equal to the given one so that they share one side. So we have another one here, and we have to make them equal. Maybe we can start with a circle. We're going to start with another circle here. And then draw a line from here to here, and we have similarity here, so this should be the same angle. Okay. I think we have another one that we can do. Because we can go from here to here instead. And then do it this way. Okay. That one's much easier. Contradiction is not a sign of falsity, nor the lack of contradiction is a sign of truth. Again, from Pascal. Cut rectangle. Construct a line through the given point that cuts the rectangle into two parts of equal area. Alright, now we're getting into area. We have this point here, and now we have to decide how to cut this so that we have two equal points of area. I feel like there's a, what was it, like the sandwich cutting theorem? Where it says that if you can cut a sandwich into n pieces, n equal pieces, where n is the number of dimensions, with n cuts or n minus 1 cuts. Or something like that. Okay. So how do we decide that we have equal areas? That is a good question. We can go into explore mode. This is what we expect to see. We can start with a circle. I don't know what this does. And then we have this point here. Can I bisect this? No, that's not going to do anything. Where do we even start? So we have this line, and it can go anywhere. Now, obviously, starting with the line from there doesn't actually work. But we can maybe start with these. Ooh, that's an idea. Start a circle here, and then start another circle there, which means the points between these. It's not quite it. I don't know what that means though. Alright, maybe let's play around a little bit and see what we get. The only thing that really makes sense is to have points from the circle or the rectangle to the point somehow. But I'm not gleaning any insights from this. Or maybe we have to figure out how to cut the rectangle into two. And we know that we can cut the rectangle into two like this here. Oh, okay, I get it. We can cut the rectangle into two parts, and we can find the midpoint here. And then the anywhere where we have a line from the midpoint outwards, the line will split it into two parts of equal area. Which means that from the midpoint to this line, or to this point here, we should end up splitting the rectangle into two areas that are equal, going through the points. Right, okay, that's how we do it. Measure twice, cut once, proverb. Drop a perpendicular. Drop a perpendicular from the point to the line. So one easy way to do that, I think, is to create a circle and then perpendicular that way. So that gets us to 2. But I think, so we have 4 elementary moves, which means we can probably reuse some stuff. So we have a circle, and we still need that. This here still gets us 4, because that's exactly what the bisector did. So that can't be right. I don't think this is going to do anything either, because we need 2 points on the line. Or maybe we start from the line. We need to draw one more thing. Ah, okay. Why does that work? Knowledge of which geometry aims is the knowledge of the eternal. Okay, so this works because this side and this side are similar. They're just mirrored. So this point away is going to be the same distance from this point as this point here. And then same thing with this one, which means that because you have the 2 points the same distance away, this is going to be vertical, which means it's going to be perpendicular. Okay. Yeah, I think that makes sense. Erect our perpendicular. So we have to do that from the point on the line and create a perpendicular out of that one. That's a little bit harder, I think. Or maybe not. You take this angle bisector tool, and then you just bisect the 180, and you get into 90. So that's 1. But how do we do that with a with minimal elementary moves? We can create a circle. Sure. That gets us to 4. But we need 3. So we need to... We're probably going to be creating 2 circles and a line. No, I probably won't have anything as imprecise as that. This is 1. This is now 4. Now, that's the same thing as what we did earlier. We create a line. Then we can maybe create a bisector from that somehow. Well, actually not, maybe not a bisector. Doesn't make sense to put random lines anywhere else. Not really. So unless you can get the same distance from here, Because you're going to need to construct a perpendicular here. It has to intersect the line. So we have another one circle here, another circle here. That's not really guaranteed to do anything. Okay. It's time to explore, I guess. Well, that's 1, that's 2, that's 3. It still doesn't get us anything. We can create a line. That doesn't really help. Who knows? We're gonna move on. Tutorial, perpendicular. You have discovered the perpendicular tool. Click on the line, then on the point. Click on the line, and then the point. Note the perpendicular tool costs 3 elementary moves, and we have no idea how. Just a reminder again, if you want to try this out for yourself, the link is in the description. I highly recommend racking your brain on this. 2.8, tangent to circle at point. Construct a tangent to the circle at the given point. So a tangent is a line that intersects a circle at only one point. If the line is at any other angle, it will intersect it at... if it intersects the circle at all, it'll intersect it at 2 points. So the tangent has a very specific slope for that intersection point. Well, one way we can do this is create a line here, and then drop a perpendicular. And the very specific slope is the perpendicular, or it's the line perpendicular to the radius, or to the diameter. Man's wandering, let him study the mathematics. Francis Bacon. Okay. But this costs 4. We can get down to 3. Or at least it should be possible to get down to 3. But considering that I don't know how to do that, or I don't know how to get down to 3 with the perpendicular tool, I'm not too optimistic that we can do this. So we somehow need to find the... Somehow need to find this line here. We only really have 2 options. One, we can start with a line. And then a circle of some sort. The only two obvious things that I see is that we have a line... Oh, don't put it there. We have a circle from this point to the midpoint. And then... something. Or we have a line. I suppose we can create a chord. But at this point we don't have any parallel constructions. We haven't learned that yet. I think we're going to move on. I have no ideas. Circle tangent to line. Construct a circle with the given center that is tangent to the given line. So the same thing, but in reverse this time. We have a line, and we need to get the circle for it. And now we have this this point here, and we can't just do this because we don't know if it's going to be exact. If this is going to be parallel or perpendicular, because that could intersect at 2 points, and unless you get the perpendicular, it will intersect at 2 points. So we can construct a perpendicular, and then if I could click properly, create the circle from there. Oh, I guess that's it. Okay. Intellectual labor in math lessons is the touchstone of thinking. Vasily Tsukomlinsky. Okay, that was pretty easy. Circle in rhombus. Inscribe a circle in the rhombus. Our goal here is 4 tool moves and 6 elementary. I don't know if we're going to get the 6, but we can probably get the 4. So we know the center is here. Oh, but maybe like last time, we can actually get the perpendicular. Oh, that doesn't actually work in rhombuses. Okay. It works in squares and in rectangles because they're 90 degrees, but they don't work in rhombuses because they're not. Okay. So we can get the center of the rhombus by doing this. So then I think if we take the midpoint, okay, maybe not. That overshoots. But we can drop a perpendicular. And so this allows us to have the perpendicular, yeah, so we have a point and a line. And so when you inscribe a circle and it touches all the sides, wherever it touches the side is going to be, that line is going to be a tangent. So here we go. The mathematician's patterns, like the painters or the poets, must be beautiful. The ideas, like the colors or the words, must fit together in a harmonious way. Godfrey Hardy. Yeah, and so we know this has to be a tangent because it only intersects at 1 point. If it were not a tangent, then it would intersect at 0 or 2 points. Yes, okay. And we had learned before that tangents are always 90 degrees to the radius. Chord midpoint. Construct a chord whose midpoint is given. So, the easy solution, take this line and drop a perpendicular there. Oh, that's it. Okay. Study mathematics like the Nile begins in minuteness, but ends in magnificence. Charles Colton. Okay, so why does this work? So a chord is a line that passes through the circle at 2 points. And the midpoint of the chord will, because of how circles work, will intersect with the radius of the circle. And so if you drop a perpendicular to that to the radius, you will end up with the chord. Because it has 2 equal parts, it has to be it has to be perpendicular? I don't remember how that goes, but yes. Triangle by angle and orthocenter. It's one of the centers of a triangle. construct a segment connecting the sides of the angle to get a triangle whose orthocenter is in the point O. Orthocenter being the center that you get when you take the what was it? If you construct lines that are perpendicular to the side that intersect the opposite vertex. Okay, so we can start with that. We get this line and we take this. So we know it has to point to that. And we do that again. And then now we can construct this line here. And that's a triangle. How do we get that in 6? I guess we'll find out. Or maybe not. A mathematician is a machine for turning copy into theorems. Alfred Régnier. I feel like that quote's been modified. I don't know if they were the original, but I do hear a lot of variants of that quote. Like a programmer is a machine that turns copy into code. Okay, so restarting. How do we get this in 6? I think that might require knowledge of how do we get the perpendicular in 3. Because that means we end up sharing one of those circles that it ends up using. So we might not actually be able to make this. Yeah, I have no idea what I'm doing here. Gonna move on. Intersection of perpendicular bisectors. Construct a segment connecting the sides of the angle to get a triangle whose perpendicular bisectors are intersected in the point O. Alright, what are they asking for here? Construct a segment connecting the sides of the angle to get a triangle whose perpendicular bisectors are intersected in the point O. So, in perpendicular bisectors being the bisectors of the sides, so a line that is perpendicular to the side that splits the line into 2 equal parts. And you get all those, and they all intersect at one point, this point O. I don't remember what significance this point has. I'm sure it has something. But we can get that with 2 tools, which should be very easy. Well, I say that, but that might not actually be the case. Actually, no. So we can get the bisector, or we can get the perpendicular here. We just need to turn this into a bisector. Does that mean that... No, it's of course not. But being a bisector means that this has to be one point, and then we need the other one. Wait, we can get this in 2 elementary moves. How? So we're trying to find this point and this point. But we don't know these points. So I know we can drop a perpendicular to do this. And then we can do an angle bisector. No, angle bisector isn't going to do anything. Because we need to work in 90-degree angles. Then you have a circle. From this point to this point, that's how you get this one. And then you can get... you can get another one. Because now that you have this point, you can drop another one here and do the same thing with this circle and then connect those two. So that's 4. How do you get down to 2? Well, let's get that 1 star first. Drop the bisector. And drop another bisector here. Draw the circle. And draw the circle here. And then connect these 2 points and we get the triangle. Well, that's 5 tool uses. Knowledge exists to be imparted. Ralph Emerson. I think we should at least get one of the other stars before we move on. Even if we don't get both, I think it would be good to get at least one. How? So how do you extrapolate the midpoint here to get down here? Because we have no intersection point here. This could be anywhere along the line. Can you use this? Okay, what properties do we have here? What properties do we have here? So we know that this angle here... Actually, no, that's not necessarily bisected either. Yeah, if only it was that easy. No, it's not going to do anything. Construct a segment connecting the sides of the angle to get a triangle whose perpendicular bisectors are intersected in the point O. So 2E means that we actually end up drawing a circle, maybe from here to here, to these points? What? How does this work? Why is this a thing? Okay, well apparently that's the significance here. The ortho center, or not the ortho center, the intersection of perpendicular bisectors of a triangle is the midpoint of the circle that circumscribes the triangle. I don't know how that works, but apparently that's a property. Okay. Interesting. If anybody can dig up a proof of that and drop it in the Discord, I think I'd be interested in reading that. Discord, by the way, if you're not in the Discord, the link is in the description. We've got a bunch of topic channels. One of them is not math, but if there tends to be a lot, if there becomes more math discussion, we might make one. Otherwise, you can just drop it in general, or Penbu Live. 3 equal segments. Given an angle ABC and a midpoint M inside it, find points D on BA and E on BC and construct segments DM and ME such that BD equals dm equals me. The diagram here is going to be a lot more clear than those words. But basically what we have here is that we have a point M, and we have to draw lines so that the 3 line segments are equal. How do we do that? Well, we know that for things to be equal, we have a circle. And so from this point, so we have 2 basic circles here. We have one circle that extends from here to somewhere on C, and then we have another circle that extends from here to somewhere on A. And these 2 circles should or have to be the same size. Now the question is, how do we get them to be the same size? Oh, does this mean this has to intersect at one point? Actually, I suppose the angle doesn't matter here. How do we, okay, how do we even get that? Is this, so alternatively, it means we need to find the circle. We need to find a circle that intersects both B and M, which means that we can get the bisector here, and then we just create another circle here. So we know that because this point and this point and this point are the same same distance away from the midpoint of this circle, that means that this point, the circle that passes through this point and has a center M, is also the same size, which means this intersection here, or these lines here, should be equal. Okay. We did that in 5, we need to get it in 4. And I think we actually don't need this line, whatever this line was. Actually, no, we do need one, because that's the bisector. Because we need to know what the midpoint is to be able to do something with it. But we don't actually need the other circle. Then we can just do this. Okay, so that's 4. And apparently that's 6 too. Are there any other lines? Yes. Given an angle ABC and a point M inside it, find the points D on BA and E on BC and construct segments DM and ME such that BD, DM, and ME are equal. Now, perhaps from the diagram, it's implicit that they should be a non... What's the word I'm looking for? Is it reflexive angle? They should be obtuse. Or concave? Yeah. I don't remember what the term is. But basically not going this way. Maybe there is just one here and there's no V. That's probably likely. Okay. Moving on. Circle through point tangent to line. Construct a circle through the point A that is tangent to the given line at the point B. Okay. We're not given a center. But we do know that if we have a bisector here, this should give us a center somewhere along this line. And because it's a tangent, that means that it has to be perpendicular to this line, which means this is the center. And we can draw a circle from the center point to the 2 points. I think not knowing how to get the perpendicular in 3 lines is, or in 3 elementary moves, is really not helping us here. Because I think knowing that is the key to sharing some of the circles. So I'm not even going to bother trying with the 6, because we need to figure out how this works. Midpoints of trapezoid bases. Construct a line passing through the midpoints of the trapezoid bases. Okay. Well, midpoints are easy to find. We can take the bisector and then draw a line between the two, and we get that. But we can do better. We can do this in 5 elementary moves. Somehow. And so we stick with just circles. Right, so this ends up being the bisector for this one. But then I don't know, what can we do with that? Because these otherwise feel like they're unrelated. Are we able to share circles anywhere? So if we do this, and then construct the bisectors manually, no, that's not right. It intersects over here. How do we get this point? We know that this is the center point. Well, how do you get that without bisecting it, though? And then what is this? Okay, I'm gonna restart that, go back into here. This point, I don't think this is special. Doesn't look special. This sort of makes sense because so they'll only intersect at one point because this is bisected, which means these two radii are the same. But that doesn't really help us. And we have no way of knowing we're over here that this point actually is a thing. And then same thing with this. We have no way of constructing that without knowing what this line is. Yeah, I don't know. We're gonna move on. Angle of 45 degrees. Construct an angle of 45 degrees with a given side. So 45 is is half of 90. We know how to get 90. That's perpendicular bisect or perpendicular, and then we can bisect that angle here. We get 45. And then we can construct the other one. On the other side. Now, how do we get this in 5? That's a good question. So we know that it is half of 90. And that probably means sharing a circle with the perpendicular tool and also the angle bisector tool. And again, we don't know how to get 3 from the perpendicular tool, so this may be a non-starter. We know how to get 60. 60 is not going to help us. It kind of does. It does in that we get another 60. Alright, we extend this line here. Then we get another 60 here. Actually, it doesn't help us. Then if you take the bisector here, right, because they're all the same. Oh. Oh, no, okay. The perpendicular bisector and the perpendicular tool both are 3. Wait a minute. Is that how you do it? We're gonna go back to alpha. Not the inscribed square, where is it? Maybe it was in beta. Perpendicular. No, I think we tried this earlier. It didn't, there's no way to get to, rather, we couldn't figure out how to get to 3. Because we need this initial circle so that we can say that this is the bisect. Like the initial circle is how we determined that, or how we constructed 2 points that are the same distance away from each other. But without that circle, then can we just how do you do this without the circle? No, because the last one has to be aligned. So you have to construct 2 things that result in an intersection that crosses this point, which means that you have to build something, probably a circle, such that you have a perpendicular line. Maybe you actually start with a line. But a line doesn't really make sense. I don't know. We're gonna go back. Go back to gamma. Go to lozenge. Construct a rhombus with the given side and an angle of 45 degrees and a vertex. So we have a line segment, and we need to create the rhombus. So a rhombus has 4 equal sides, and the opposite angles are equal. Which means if we construct a circle, not that way. If we construct a circle, then we can double this angle and get the other one. Except we don't have an angle. Oh, but we do want an angle of 45 degrees, which means we can draw the perpendicular here and bisect this angle to get to 45. And then now we know that because this is 45 degrees, this is 45 degrees, we have 100, I think it's 135 in the middle there. 180 divided by 45. Or sorry, 180 minus 45 degrees. And so we can draw another circle here to get this point somewhere around here. No, that's not quite right. It's this point, actually. And so where these two intersect, because we're looking at this being the one side. That's our lozenge. And we spent too many on that. But we can construct another one in a similar fashion. So we already have this one. And we can construct the perpendicular. Or sorry, the angle bisector. And then where this one intersects is where we can put the other one. How do we get this one? We got a circle there. Okay, I didn't expect to do that one, but sure. There we go. We got 4 of them. But we're going to try for 5L. I don't know if we can do 7E, but we can do 5L. Probably. So we know we need to get a 45 degrees. And we can do that by dropping the perpendicular and then bisecting this. That's 2. And now we have 2 sides. Now we get 4, or rather we need 2 more for the 2 sides. Which means we have 1 more tool that we can use to calculate the opposite corner. We can bisect. Now, if we bisect, we can get the other corner, but because this is going to be like this corner here is always going to be at an angle that bisects this angle here. This is also 45. But I don't think that helps. Actually kind of... No, it doesn't. It doesn't help. But at some point we learned how to double an angle. And now I don't remember how we did that. We had a line. We had a line. Okay, we're gonna go back to the double angle one. So if you create a circle here, and then create a circle from there, the point where this intersects is where it doubles. Okay. So if we apply the same thing to the other one, if we drop perpendicular here, and then bisect this angle, that gets us 45. Actually, no, that doesn't work because double of 45 is 90 degrees, and that's not what we want. Also, we have no angle on this side anyway. So this is 4, which is not going to work because we need one more. Can we use a bisect tool? Or not the bisect tool. Can we use the angle bisector? Put a point inside, bisect this. Which is actually not going to help. I don't remember if I ever did actually solve this one. But you can get this, and then you can get this, and then you can get this. But that gets you to 5. But now we know all the points here. So I don't see how to get 45 degrees without doing these bisectors. And if we do another one, that gets us to 3. And then the rest of them would have to go to the 2 sides, which we can't afford. But then we know that this point and then this point, or well, I guess we don't have the other points. Can we construct that? No. We're gonna move on. We did get 1 extra star already, so I'm gonna count that. Center of a quadrilateral. Construct the midpoint of the segment that connects the midpoints of the diagonals of the quadrilateral. Midpoint of the segment that connects the midpoints of the diagonals. We have a diagonal and we're trying to, we need to bisect the diagonals, and then we need to connect them, and then find the midpoint of that. So, let's start with that description. We have the 2 diagonals, and then we try to find the midpoint of those, so we can bisect these, then we bisect the point in the middle, and then we have that. And we do have some redundancies there, so we can cut down on that. So if we don't actually draw the diagonals, then we can get this. But then, where's the thing? Maybe we do need this? But then we're just back where we started. Can we do this with circles? What significance does this even have? Okay, let's play around with this a little bit. Because this feels like it's in the middle of something. Okay, so it's not the intersection of bisectors. And I don't think it has to do with these sides here. I'm going to draw perpendiculars to, maybe that doesn't actually do anything either. What happens if we drop a perpendicular from here to this line? I don't think that does anything. Hmm? So what happens if we bisect these angles instead? Angle bisection, I think, gets us the... Not that one. Surely not. Because that's going to differ depending on which one we end up, which angle we end up bisecting. Yeah, that doesn't pass through the point stall. Okay, what else do we have? What even is this? It's not the midpoint of an the square that is inscribed. The circle that's inscribed. So create a diagonal, create a diagonal. Oh, that's not diagonal. Create a diagonal. We bisect the two. And then we bisect... What relationship does this have? No, that's not on the line anyway. This is on the line. And then that is the midpoint of that. So if you can find a circle that... You can find a circle that that intersects those points, then you find the midpoint-ish. No, but that can't be right. Then you don't actually have that. You have this circle, and you have this circle. Doesn't help. Or L. How do you use 4 tools to find that? I think some lines that we have are probably redundant in some way. But how do you go down from... Well, what do we have? 1, 2, 3, 4, 5, 6, 7, 8, or whatever it was. How do you cut down to half of that? I think you do use maybe exclusively this, or almost exclusively this. But you need to find some way to intersect that. We're gonna move on. Double segment, because these are gonna get even harder. And if we end up getting stuck too much on these early ones, we're not gonna get to the later ones. Double segment. Length of AC is twice the length of AB. Construct a point C on line AB such that the length of AC is equal to twice the length of AB using only a compass. Using only a compass. Okay. We have no straight edges, because otherwise this would be easy. You take a line, or you draw a circle from B to A, and then you draw a line through it, and then whatever comes out at the other end is where it is. But we can't do that. Although I think we did do this earlier. Or we make these 3 circles here, and we make this point here, and that's the other side. And I think we can do it on the other side as well. We do it from A, and then we do this, then we do this, and then we do this one, we get the other side here. And I guess that doesn't actually count. Yeah, okay, that makes sense. Which is fine. Wait, 3L? How do you get this in 3? We took 5. What? Okay, so the only thing that you can do, really, the only thing that I see that makes sense anyway is to draw 2 circles here. But apparently that's not the way. But you can do this. I see. A mathematical truth is neither simple nor complicated in itself. It is. I don't think I understand this quote. A mathematical truth is neither simple nor complicated in itself. It is. Oh, no, I still don't get it. Emily Lim 1. Okay, so why does this work? Actually, we can do this other one, or I guess it doesn't recognize it. Why does this one work? So we know that this is right in the middle of AB. And so if you have a circle that has the radius of this thing here, I mean, I don't know what this is. Why? Yeah, I don't understand this one. Actually, oh, hold on. So we can figure out what this length is. So if this length is AB, that means the length from here, or from here to here, is AB, which means this is, if you cut it down the middle, you have Pythagorean's theorem. This length here is AB divided by 2. This is AB, which means this is something. So AB squared. So Pythagorean's theorem is A squared plus B squared equals C squared. C here being the hypotenuse, which is AB. And then A being AB minus, or AB divided by 2, and you square that, and so you get length of AB divided by 2, AB squared divided by 4, plus this, which we're trying to figure out, and so you get, if you solve for the other side, we have AB squared minus, only I could write this down. Actually, wait, maybe I can write this down. Hold on. What's that one program? GeoGebra, which I might not have here. Let's install that. Okay. Apparently I can't, oh, wait a minute. Yes, I still can. I think I still can. Alright, we are going to switch to desktop mode. And we're going to try this out. Switching to desktop modes. Oh, this is desktop mode. Okay. Thought I was on game mode. But we're going to plot this out. We're going to bring this in here. This program is called GeoGebra. It is a... I don't know how I describe this. It's one of those graphing calculator kind of things. Okay, so we have a point A and B. We have points A and point B. So let's make them 1 apart. And then what do we have here? We have a circle. Let's draw a circle. Circle with center through points. Like this. And we had another one like this. And we had D. The intersection here from there to there. And we have this line segment from here to here. Well, let's make that a line. You have this intersection point here and this intersection point there. All right, and we can measure what this is. I'm gonna move this over a little bit. And then we also had a circle from point C to point D, where then this is that. Okay. So I think what we need to try and understand is why this is perpendicular. Why this ends up intersecting on the perpendicular. By doing this. So this line segment here, we have a segment here from C to E is 0.87. Which is the result of... Wait, why does that work? So it's C to D. Why is that not 1? Oh, right, because it doesn't make sense for it to be 1. This is 1. This segment here is 1. This segment here has to be longer than 1. Okay, I think I'm starting to confuse myself. I'm going to move on. Angle is 60 minus... Or angle is 62. Construct a straight line through the given point that makes an angle of 60 degrees with the given line. Okay. So we'll start with the circle. And so we can start with a circle. I don't know where this goes. Now, I think this is where things start to get hard. What do we have here? We're at Delta. We have 10 of these. We're coming up to 2 hours. We might try to go through some of the stuff in Delta if we can solve them, and then stop there. Man. Okay, we can draw a perpendicular, maybe. Then we can draw a circle from the point to the line. Sure, what does that do? We can draw another circle from the point to the... or from the line to the point. And because this we know is 60 degrees, that means that we actually need half of that. So this here is 60 degrees. Okay. The best angle from which to approach any problem is the triangle. Author unknown. That's a bit of an enough moment. Okay, sure. How do we get down to 3? So if we drop a perpendicular, we'll create a circle from that. You can do this. No, that's not quite right. What even is this angle? That's the wait a hold up. Wait a minute. That's a 45-degree angle. Wait a minute. That's a 45-degree angle. Did we just solve the other one? $45 degrees. I think we may have solved the other one. Or like this one. Well, sort of. That's actually more than what we had before. Oh no, that's how we get the okay. That's how we get the elemental one. What do we do here? Okay, sure. So we drew a circle that intersects this point at its circumference, which means that this is 45 degrees because why? I can't say I fully understand that either. Oh, no, because these two sides are equal. If these two sides are equal, which that means that these two angles have to be equal. And if this is 90, that means that the other sides have to be 45. Okay, that makes sense. Does that help us with anything else? I think that might help us with this one. So if we drop a perpendicular here, and we create a circle here, that means that we get this 45-degree angle there. But then that uses 3. That uses 3, which means we have 2 more, which would be for the, well, we don't even have this point here. Okay, I don't think this one helps us too much. Because it would be around here somewhere, I think. This I don't think quite works. You need to bisect this angle to get 45, but that's not what you're looking for. Yeah, I don't think this one helps us with this one. The angle is 60. Can we do something similar here? So we'll start with a perpendicular. Oh, we'll start with dropping the perpendicular. Let me draw a circle. Or maybe we don't draw a circle. And that's what we did earlier. I don't see any other thing that we can do other than drop a perpendicular here to get any sort of precision or accuracy. That's 1. That's 2, which we know isn't going to do anything. That's 3. And I don't think this is 60 degrees. We're going to move on. Circumscribed equilateral triangle. Construct an equilateral triangle that is circumscribed about the circle and contains the given points. Okay. So we know that these have to be tangents because they only intersect at one point. That's what it means to be circumscribed. So we know that this has to be tangent, which means that we can drop a perpendicular, or we can draw a line here and drop a perpendicular to here, and that's 1. And we know that the other vertex has to be... It's an equilateral triangle, so it has to be along this line. Which means that we can draw a circle. We can draw a circle so that we get 60 degrees somewhere. That's not how we get 60. This is 45. 60 would be around here. Okay, we gotta find a way to get 60. So how do you construct 60 from this line here? We know how to get 60 though. Well, I mean, maybe. I don't think so. Yeah, I didn't think so. How do you get 60? Wait, hold up. We know that this has to be the midpoint because this is an equilateral triangle, which means this has to be the midpoint. We need to find 2 points here that are the same distance away that end up having to intersect there somewhere. We know how to construct a 60-degree angle given a line and a point. Except we can't have that intersect. It has to... We actually only need 2 of these. Well, only one of them, really. I'm still a little bit confused. We have one of the edges, and we just need, and we know that the other vertex has to be in here somewhere. On this line somewhere. Okay, I'm gonna turn this on. And we're gonna explore. Because we know that we have this, and then we can drop a perpendicular to get this. And then actually we can create stuff inside the circle. Like this. I don't think that... Oh, that might be an insight. We have this point and this line, and that... I think that gets us to this point here. I don't know why, but apparently it does. So then we just create a 60-degree angle from there. and then we can get this point. Okay, so we'll start with that. We have this, we drop perpendicular. We do this. Not quite what we had before. And then we find the tangents from here to here. Is there any way we can do that without having to draw more circles? Can we do something like this? I don't think so. Oh, wait a minute, hold up. We do have this, and then we have the other side too. We just need to find the point in here. So we need a way to get one of the points on the circle. So either we create a 60-degree angle here, which I kind of don't want to do. So either we create a 60-degree angle here using the previous construction methods that we had, or we try to find the point on the circle that ends up being tangent to this line here, or the tangent that passes through this point, which there is only one. There's only one tangent that passes, or sorry, two. We already have the other one. We already have the other one. Can we use this line somehow? Is it perhaps the perpendicular? Oh, no, of course not. Okay. Is it perhaps this here? That's also a bit of a long shot. Okay, so maybe we do have to construct the 60 degrees. How did we construct the 60 degrees last time? We did this. Actually, I kind of don't remember how we did that. It was 60 degrees from this side here. That means that we had to create a 30 degrees. We had to create 30 degrees out here. We don't know where out here is. We're trying to find that. Oh, but we can do 60 degrees from here, which means we can do this. And then we can get 60 degrees from here. That can't be right. Is this not 60 degrees? Construct an equilateral triangle, which means the corners here do have to be 60. So then the question is, if we construct this way, why is that not 60 degrees? Because this is how you construct an equilateral triangle. Oh, no, but it is 60 degrees. I see. So it is 60 degrees, but the problem is that it's too far away. Okay. So where did I get this from? Apparently nowhere. So we gotta find something where we can do this, but somehow it intersects with something. Because if we do this... Oh. Oh, no, that... Wait a minute, hold up. No, that makes sense. Oh, that sort of makes sense. I don't know how to construct that, though. So what we have here is that we have a circle. If you draw it from here to the points here, or to one of the corners, it ends up intersecting the circle, given circle, at the tangent points. I don't know how we can use that. But then the question is, what is this? What is this and what can we do with that? So we draw a circle here. We draw another circle. Oh. That's how we get 60. Okay. We draw this circle, draw this circle. And we draw this circle. We draw this line. Not that line. Draw this line. We drop a perpendicular to that, which is over there, so we don't actually need this line. We draw this line, because you know that's perpendicular. Or, yeah, perpendicular here. We have this tangent here. And then we know that this opposite side has to be that, and we have this too. Okay. Can we pare that down even more? Yes, we don't need this line. So we draw a circle here, draw a circle there. And then we know that this has to be that. We can draw this line, we draw this line, and draw this line. That's 6. That's 6 elementary, so we got one of these. Can we do even more? I think we do still have to start with this. But then... well, we can maybe try this, and this gets us 2. But then we already know that there. I don't think that helps. We can get the bisector here. I guess we don't need a bisector there because we already have the... Oh. No, that doesn't do anything either because it's the same thing. If you draw a line from here to here, and then you draw a line from here to here, not there. How do we get this point? We got this point by doing this. We can draw a perpendicular line here. We can draw more perpendiculars. The problem is, that's not actually going to help us. We need the other one here. Okay, well we got the elementary ones, so we're gonna move on. Equilateral triangle in circle. Inscribe an equilateral triangle in the circle using the given point as a vertex. The center of the circle is not given. Okay, so this is the opposite, where instead of constructing a triangle outside, we're trying to construct a triangle inside. We don't know what the center of the circle is, which means we are at a bit of a loss. But all we can do really is maybe create a circle here. We can find the center of the circle. By doing this twice. So we can bisect the chord twice. We get the center of the circle. And then, is there something that we can do with that? Maybe. Well, but also maybe it doesn't matter. Well, it does in that we know that this is 60 degrees. Or at least I think we do. I don't think that's 60. Okay. Considering that this is 3 equal chords, this probably trisects the circumference of the circle. So we're looking for 3 points that are equally spaced apart on the circumference. We can find the center, sure. I don't see any other options really. So that's 2. How do we get this in 5? Or how do we get it in 6? Or how do we get it at all? I think we should start with getting it at all, and then we can work on optimizing it. Okay, so let's find the center. We can start with that. So we know that this is the center. And then from there, we know that this has to be one of the vertices, which means that if we draw a line from here to here, then some perpendicular line to this line is going to be one of the sides. A perpendicular line to that is going to be one of the sides. Okay. What does that mean, though? Can we use a circle somehow so that we get all of the... I don't know how we can use that. Because yes, we can do this. But this is not, as far as I know, 60 degrees. Maybe it is. Okay. So we're gonna restart that. But we need some way of knowing the center first. That's what we need this for. And then we have the circles here. That's already... We're exhausting all of our all of our moves just to figure out where the points are. So this can't be good. Okay, we're gonna play around with this here. We know that this is a thing. But we also only know this. Okay, can we have the points on the circle? Are we able to just... No. How do you do this in 5? Or how do you do this in 6? I don't know. For me, I think we need to find the center first. But to do that, we would have to bisect the circle. And that already takes up a whole lot of tools. We're gonna move on. Cut 2 rectangles. Construct a line that cuts each of the rectangles into 2 parts of equal area. Oh, maybe that was the sandwich theorem. So we learned from last time that if we take the midpoint, if we find the midpoint, then any line that passes through the midpoint will cut the rectangle into 2 parts. So all we have to do is connect the 2 midpoints and we get that. Mathematics is the most reliable form of prophecy. William Shovel. Yeah, okay, this one was pretty easy. How many more left? We got a little bit more. Square root of 2. If you didn't realize you can calculate lengths here, it is certainly something we can do. Let length of AB equals 1. Construct a point C on the ray AB such that the length of AC is equal to the square root of 2. So, one thing to recognize is that the square root of 2 is the length of the diagonal of a square of length 1. So we construct a square of length 1 such that this ends up being the diagonal, which means we're looking at 45 degrees to this thing. Looking at another 45 degrees here. Or not 45, we'd drop a perpendicular here. Alright, so these are now our square edges. And then we can calculate the other side. Which actually I don't think we need this. We don't need this. We don't need the perpendicular, because we only need the one side. And so then if we take this, this should be the same length as this one. Which means that a line here to here is going to be the same length as this one. That creates a square. And we can take this point here, and that is our AC. The square root of 2 is also known as Pythagoras' constant, probably for that reason. Can we do this in less? Supposedly so. I don't know how. how do you get this point with 3? So last time we dropped it perpendicular. Oh, that's too far. This is too far. We need something smaller. This is 45 degrees. And this one we did earlier. This gets us to 4. How do we construct 45 degrees without this perpendicular? We did that by creating a circle. It's a little bit shorter than that. Okay, we're gonna move on. Square root of 3 lets AB equals 1 construct a point on the ray AB such that the length of AC is equal to square root of 3. Now, what is the square root of 3? It is saying that if we look at the Pythagorean theorem, we can construct a triangle out of it. Then it means that 3, or what was it? It ends up being, what is the square root of 3? 3 is equal to x squared plus y squared. And so that's the square root of 2 plus 1. If AB is 1, that means that we have a length of side 1, and then we have the other side being the diagonal of a square that has side 1. And then C is whatever that length is going to be. Okay, so let's start with that. We'll start with a circle. And we create a diagonal out of that. And so this is a diagonal. I don't know where we're supposed to do this actually. So we have one, and we need to construct a triangle. We need to construct a triangle. What am I looking at? This is not where I should be looking at. So we need to construct a triangle. This is 1. This is 1, or this is square root of 2. But the 1 needs to be at a right angle from this one. No, this is square root of 2. This is 1. So we draw a perpendicular one here. That means that this length here is the square root of 3. Which means we can draw a circle from here to here and draw a point here, and this is the square root of 3. Square root of 3 is also known as Theodorus constant. Theodorus constant. Okay, so to illustrate this again, what do we do here? Well, let's draw more lines so that we can show how this works. We created a circle of size 1. Actually, let's do this in GeoGebra so that we can see a little bit more clearly. Delete all of that. So we had a line segment, or we had an array from here to here. AB is equal to 1, and so we created shift. Yes, shift. Okay. We created a circle that intersects that has a radius of 1. And then our goal here was to create a a square that had a diagonal, so that we can create a length of square root of 2, because the square root of 2 is the length of the diagonal of a square. And so then we created that one here, our line segment here, from this intersection point to this intersection point. So G has the length square root of 2. And then we can create another circle from that. Created it here. So that now anything that's within here, right, is now the square root of 2. And then what we did after that was that we took the length. Oh, don't do that. I'm trying to figure out what we did here. What did we do here? So we had the square root of 2. We did this. And then we took the perpendicular. We took the perpendicular line here. If I can figure out how to get perpendicular. I think I need a line segment from here to here. Oh, no, don't do that. Then we take the perpendicular. Here. And so, in effect, what we did was we created a triangle of length 1. This is AC. And then we created, this is one side with length 1, and then one side with length square root of 2. Right, because this circle is square root of 2, and this circle is square root of 1. So we created a triangle, a right triangle, with that. And so then this segment here, the diagonal, the hypotenuse, is now the square root of 3, because Pythagorean theorem says that a squared plus b squared equals c squared, a being 1, c being the square root of 2. So 1 squared is 1, plus 2 square root of 2 squared is 2. So 1 plus 2 is 3. And then c squared being 3 means that if we isolate for c, then we get c equals the square root of 3. And so now this length is the square root of 3. And then we can just draw another circle from here to there, that intersection point. And then because of the circle, then that means that on this ray, this point here is the same distance away from here, or as this, which means this is also the square root of 3 away from A. A little bit involved. How do we do that in fewer moves? I don't know. At this point, I feel like I don't really want to find out, or don't really want to try to figure it out. But moving on, we do have a few more left. I think at this point we're just going to try to solve them. Construct an angle of 15 degrees with a given side. Now, 15 degrees is half of 30. So an easy way to do this is we take the perpendicular, we bisect the perpendicular, and then we bisect again. So this gets us 30, and this gets us 15. And I think I messed up my bisectors. I'm going to generate a point here. So drop the perpendicular, bisect, bisect, and bisect again. I'm doing my math right here. Oh wait, no, this is wrong. Because perpendicular is 90, and you actually have to divide by 3 first to get 30. What we're calculating here is 45, and then half of 45, and then half of that, which is not 15. Okay. So then we can construct a 60-degree angle. Bisect that, and bisect that, and we get 15. If we know anything, we know it by mathematics. Pierre Gassendi. And then we can create a double angle here. And we get the other 15 degrees. How do you construct this with just 3? Or 5? So it means we aren't going to be bisecting a whole bunch of stuff. So this means that there has to be a way that we can just do it. Wait, what is this angle here? Hold up. I think I do want to try that out. Well, it feels kind of... So I know this isn't 15. That's 30? Okay. I don't know why that's 30, but okay, that's 30. What does this mean? Wait a minute, didn't they ask for 30 degrees in one of the other ones? Angle of 30, that's how we do it for this one. I don't think this is what we did. This is what we did. This is how we get it into 3. I don't know why that's 30, but okay. Actually, I think we can figure that out. So the reason why this is 30 is because this here we know is 60 degrees. And we know that, so if we assign this length as 1, this is 1, and this is 2. So this is 2 and this is 1. And we know that this is going to be 90 degrees. I actually don't know why that's going to be 90 degrees. But it is 90 degrees. Which means that we have ratios as 3, 4, 5. Three, 4, 5? I think it's 3, 4, 5 for 30, 60, 90. You know what? I don't remember. There is a theorem for this, and I don't remember why this works. But if you do the math, it works out, I think. Well, like, obviously it does, but I'm not going to do that math. Can we get down to 3? Which means that there is a very similar construction that we can do for that. If this is 60, and then 30 is on this side, does that mean 15? Oh, no, duh. If that's 30, then we can do 3 like this. Okay. I don't know how we can get it in 5. But sure. We can get it in 5 by sharing one of the circles, probably. Okay, so we should at least maybe attempt it. So we can get this in 15. And then we can get this way. And this is... Well, it can't be right because that's only 4. 5 is supposed to be the minimum. How did we bisect angles again? You bisect an angle by taking the bisector here. And then we need one more. I think we need one more circle somewhere so that we can get. Oh, is it this one? It's not that one. We need another circle somewhere so we can generate this line. And it probably isn't that side. Is it over here? No. Is it over here? No. Here? Here? We don't know this line yet. No, 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 and no. I don't know. I don't know how we get to 5, but we're gonna move on. Square by opposite midpoints. Construct a square given 2 midpoints of opposite sides. So given that these are midpoints, that means the midpoint here, if we take the midpoint there, that is going to be the midpoint of the square, and then we can get this, which means the midpoints would have to lie on that side. This is probably going to be easier explained. But that said, I'm not entirely sure how this is going to play out either. So we know that this is going to be the midpoints. And so we can just drop perpendiculars like this, I guess. Well, that'll work. It's not the best way to do it. So we draw a line, we draw a bisector, we bisect the angle here. Draw a circle. We don't draw a circle. We do draw a circle. We don't draw a circle. The insight there, though, is that if you draw a bisector here, and then I need a point. If you draw the diagonal, this becomes the diagonal of the square, which means your other 2 points have to lie along this line. Question is, what do you do with that? And how do you know the points are going to be there? This looks like 90 degrees. The insight here, I think, is that if we get 4 of these lines, so 4 lines have to be taken up by the 4 lines of the square. And we have 6 of them, which means we need to draw 2 additional constructs, probably circles, possibly not circles. So that we can draw more lines. What are these points? I don't quite understand what these points are. Okay, so we draw a circle here, draw a circle there. That doesn't really mean anything. What we do know is that if you draw a circle from here to here, this point is the middle. This is the midpoint. Oh, I think we can get to 4. So we do this, and then we bisect. We draw a circle from here to here. Try that again. We do this. We take perpendiculars and draw circles. We draw a bisector, and then we draw circles. And draw circles. Doesn't work, we need more. That is the square, yes. But that gets us to 8. I feel like I'm really close at this, but I'm not quite sure where, what we're looking at. We're gonna move on. I think this is the last one in the set. Square by adjacent midpoints. Construct a square given 2 midpoints of adjacent sides. This, I think, is going to be a little bit harder. Where do we begin with this? We can take a bisector. We know that the two of the vertices have to lie along this line. And that's about all I know about this one. I think... No, I don't think I have any other ideas for that one. We can take this, and we can take this. I don't think this means... actually it does mean something, because then this here is 90 degrees. Which means we can extend this And this is now... This is now 90 degrees too. And we can create a perpendicular from here to there. Okay. Let's try that again. So we know that the we know that we have bisector. This creates one diagonal. Oh, wait a minute. Maybe we can do it another way. We can create this. And then if we create a perpendicular to this, then we get the other side. And that means that this is the other midpoint. So then if we bisect this angle, this is the other diagonal. Does that actually help us? No, well, that's not diagonal. That's the other... That's aligned through the midpoint, which means the other midpoint is on the other side. But we do know that... No, if we bisect it this way, this gets us one of the sides. Which means one of the sides is here. We can create a perpendicular. And we can create another perpendicular here. And then we can create a circle there. And we have now used too many. And that's not even the square that we're looking for. We can create this. And then this is the square we're looking for, but we still have used too many. Apparently that's not the square we're looking for. Because it still has to go through here. And that's the midpoints. I'm gonna try that again. Alright, so we create a line. We drop a perpendicular. We do not drop a perpendicular. No, we do. We create a line. We drop the perpendicular. We bisect this line. Or bisect the angle for the line. And then... we do this. And then now we know that this has to be another midpoint. Means this here is what we're looking at, and then this line here this is not looking like 90 degrees. What happened? How did I even get here? We got this here, and then we have this. No, that doesn't make any sense. I'm starting to confuse myself. But that's that. We've at least gotten through some of these. We've unlocked Epsilon. We're not going to do that today. Can we maybe get 100% on Alpha at least? Now that we know more stuff. So we know how to get the other side. We already knew how to get the other side. We already knew how to get the other side because we can do that. And now we just need a... Yeah, this gets us 8. I think we need to try to do this with just the compass and straight edge. So we can do the straight edge here. And then we can... No, we did that before though. You can get to the other side by doing not this, but doing this. But then this is useless to us because we already have we can get this in fewer steps. However, okay, we already knew that though. Like, we already know that so if we can do this, then we already know we can get the intersect or the midpoints by doing this. We can intersect that, and then we spend 4 on this, but it means that we need to draw 2 things so that we get the 3 points. Because if we're actually no, 3 things. Because we have we have an allowance of 3 elementary moves. We can draw 3 things and get somewhere. 1, 2, 3. Oh. Because this is halfway. But then this ends up spending more than what we have, or what we got before. However, now surely there's something that we can do here. We can draw a line. Then we can draw something. I don't think these help us. So from here we can do one of 2 things. We can either draw a circle from there to there, or we draw a line from there to there. The line seems like it's possibly more useful. Possibly. But as we saw here already, that isn't going to help. That actually uses more than our helper tools. What other insights do we have? I feel like we're supposed to be able to reuse a circle somewhere. By the way, chat, if you have any ideas to throw out, feel free. I do want to at least maybe 100% the alpha. How do we get this down to 7? Because we can get it to 8, but we need to drop one of our, probably one of our circles or something. Concentric circles isn't going to do anything. Interesting. Interesting. This somehow creates... How does that work? Why does that work? This is another 30-degree angle, because this is 60. But that's still too many. Because we still need 1, 2, 3, 4. This will get us to 9. Anything to do with multiple circles, I would think, might not work. How do we find the tangent to the circle? Actually, wait a minute. We're looking for 45 degrees on here. We were looking for 45 degrees. We learned how to do 45 degrees by accident. Oh, I feel like it doesn't apply in this case. Let's have another look at this. So this is... So we assume this is 1, and this is another 1. This is equated to 2. You gotta find a 90-degree angle here. Or... find a 45-degree angle here. So you can split it in 2. We're able to find the tangent here. Okay, that is an interesting property. I don't know if we can use that. I don't think we can use that. Or can we? That allows us to find that. But then that also means that we can find this. But then we can't use this because otherwise... We already know that side. So that's not actually going to help us. So we know this. we know this, and then we know that we can get 45 degrees by something that I don't remember. Okay, we're gonna go back. We're gonna go back, find the 45-degree one, and hopefully we can get some insights from that. We managed to get this. Draw the perpendicular. Not like that. This is 30 degrees. This is 60 degrees. We want 45. How do we get 45? We got 45, I think, by doing this. No, it's by finding the... We found 45 by doing this, finding the perpendicular, and then creating that. The problem is we don't have a perpendicular. We don't have a perpendicular tool. We don't have the perpendicular tool, and okay, no, I managed to find the perpendicular in 3, and I don't remember how now. Or did we? No, we didn't. We didn't figure it out. Okay. I think we might have to leave it there, because I am completely out of ideas now. Alright, well, there you go. Euclidea, there's a lot for you to mull your mind around. Yeah, good luck if you try this. It's a lot of fun. There's a lot of head scratching too. But yeah, there's a ton of levels here. And they definitely get hard. They get really hard, as it says. But yeah, definitely do give it a shot. And if you happen to solve any of these problems, feel free to drop in the Discord. Just make sure you spoiler them. And if you're not in the Discord, link is in the description. Yeah, if we get a lot of math talk, we'll make a math channel. But I think that's it. Happy Pi Day. Draw lots of circles, eat pie, whatever it is that you do. Yeah, I think that's it. Next stream. We are doing more composition. And we're going to be doing a challenge where all we do is play the note F. And that's why this composition is called F. We're going to restrict ourselves. Should be a fun one. We'll probably be doing this for orchestra so that we have a lot more sounds to play with. And this will be at 12:30 Eastern time. So that's 7 hours earlier than usual. So make sure to yeah, don't show up at the usual time because I'm not going to be there. It will be 7 hours earlier. I think that's it. Yeah, I think that's it. Thanks for watching. Go play Euclidea. Link again is in the description. Go join the Discord if you're not already there. And look forward to the next stream. Spam app. Alright, thanks chat. We'll see you next stream and good night. Happy Pi Day.